Fishing lines, running gloves, and textiles are common objects in our lives. But how do they relate to innovative medical research and hand orthoses for stroke rehabilitation? My name is Tim Guo, and I would like to introduce my exciting research project to you. According to the American Stroke Association, nearly 800,000 Americans suffer strokes annually. A common after effect is hand weakness, making daily activities like opening doors and using smartphones difficult. To help with recovery, many rehabilitation gloves have been developed, from air-driven actuators to exoskeletons using artificial tendons. These devices are all under the umbrella of soft robotics, which mimics human muscles and tendons. However, while safer and more effective than hard robotics and passive orthoses, these devices tend to be more expensive, unreliable, and less wearable than their traditional counterparts. Is there a way to combine the best of both worlds so we can make effective rehabilitation accessible to everyone? This question motivates my research. Recently, a new type of soft robotic muscle has been developed. When nylon fishing lines are heated by resistance wires, they will slightly contract due to the entropic effect. This contraction can be further amplified by twisting and coiling the fishing line, resulting in a twisted and coiled polymer actuator, or TCP. Because it can contract on its own and only needs low voltage electricity to function, it can replace the tendons in exoskeletons by eliminating external cable winding units, making the device lighter and more portable. That's a theory, but how do you make it, and does it work? To make it, we start with a 12-pound Omniflex fishing line and 2 Madeira conductive threads. Next, the precursor wires are fixed to a stepper motor and twisted. Self-coiling is induced by extreme twists, amplifying contraction. Finally, it is annealed at 200 Celsius in the makerspace furnace and electrothermally trained until its length is stabilized. 3 separate designs from the literature were tested through more than 45 prototype iterations until the current design was chosen. The current design can achieve a 30% contraction and lift 3 newtons of load. The orthoses is made from a pair of running gloves from Amazon. To integrate the TCP, we sewed 3D printed cable holders onto the glove and threaded the TCP through them in a 3-warp configuration. Polyester weft yarns are finally weaved into the TCP to complete the smart textile. In the current stage, the orthoses can achieve a displacement of 1 cm and a range of motion of 10 degrees within 40 seconds, lifting a load of 50 grams per finger while only weighing 42 grams itself, proving the feasibility of the design. It is also cheaper than alternative designs, costing only $66, including labor. The novelty of the research is threefold. First, unlike previous designs where the TCPs are mounted away from the hand, our approach integrates TCP directly into the device, making it fully standalone and more wearable. Second, polyester weft yarns transform TCP strings into a smart textile, improving heat dissipation and increasing the contact surface, while acting as strain-limiting layers to enhance durability. Third, we aim to develop closed-loop control algorithms for precise finger movements, utilizing the self-sensing capabilities of the smart textile for accessible data collection and force tracking control without expensive sensors. In conclusion, our research has the potential to make hand rehabilitation more affordable, portable, and effective. We aim to bridge the gap between advanced soft robotics and practical everyday use, ultimately improving the quality of life for stroke survivors. Thank you for watching. You can follow me on my website and socials for more research updates.